Alright, so in this presentation, we're going to talk about graphing lines a little bit more. In the last section, we talked about graphing lines that were in slope-intercept form. In this one, we're going to talk about some special lines, horizontal and vertical lines, and graphing using intercepts. This comes from section 2.3 of the textbook. So let's start with horizontal and vertical lines. These are some special cases. So let's look at each one of them. A horizontal line is going to be a line that goes left or right. It does not go up or down. The equation for a horizontal line is y equals k, where k is some number. It has a y-intercept at 0k, that's where it crosses the y-axis, and it has no x-intercept. Our domain for a horizontal line is all real numbers, and our range is just the value k. These are functions, so they can be written in function notation. So let's look at an example. Let's look at example A. Example A, we have y equals -2. I'm going to go ahead and create a table so that we can at least have 2 points in order to graph this. So for instance, we want to pick a value for x. Let's say x equals 0. What is y when x is 0? Y is -2. Let's pick another value for x, let's say 3, and you can pick whatever number you want. But when x equals 3, y is -2. X can be any number. X can be 1,345,999 times pi divided by the square root of 5. Okay, it can be anything it wants, but no matter what x is equal to, y equals -2. So if we go ahead and plot these points, 0, -2, we're going to go 2 down along our y-axis. For 3, -2, we're going to go 3 to the right and 2 down. And so we should be right about here. If we draw our line, it looks like this. We label, and we have a complete graph. So if you notice, going back to this idea of domain and range, how far left and right does this go? This goes forever to the left. It goes forever to the right. And so our domain is all real numbers. Our range, what about up and down? Well, notice this graph does not go up and down. It stays at -2, and so our range is -2. Okay, so let's talk about a vertical line. A vertical line goes up and down. It does not go left and right. It has an equation, x equals k for some number k. It does not have a y-intercept, but it does have an x-intercept at k, 0. Our domain is just going to be, what are all the possible x values? Our domain is just going to be k, and our range is all real numbers. Now, vertical lines, these are the only types of lines that are not functions. All right, so let's look at an example. Let's look at example B. We have x equals 4. Again, I'm going to create a table so that we can get some points. So we're going to get x equals 4. When x equals 4, let's say y is 0. Another point that we can put is 4, 2. X equals 4, y can be 2. And just like on the previous example, where it's the exact opposite. X is always going to be 4, and y can be whatever number you want. So you can plug in whatever you want for y, and x is always going to stay at the constant. So it's always going to be 4 in this case. So if we go ahead and plot this, we have 4, 0. That's going to go 4 to the right and stay on the axis. 4, 2 is going to be 4 to the right and 2 up. And so we should be right here. And now if we go ahead and draw our line through these points, it should look like this. We label. Now going back to our domain and range, notice that our domain, what are our x values? Our x values are always 4 on this one. Up and down, notice that this graph goes forever down, and it goes forever up, so this is all real numbers. Remember, with graphs we have our vertical line test, and as this is a vertical line test, it crosses through our graph an infinite number of times, so it is not a function. Alright, so that takes care of horizontal and vertical lines. The next thing we want to talk about is graphing using intercepts. Now intercepts, they're going to come up in our next section a little bit more, but we want to talk about just the basics. So first off, graphing using intercepts is best used when an equation is in general form, which is ax plus by equals c. So our x-intercept, this is where the graph crosses the x-axis. It is written k, 0. To find it, we want to plug in 0 for y and solve. The other type of intercept we have is a y-intercept. This is where the graph crosses the y-axis. It is written 0, k. And to find, we plug in 0 for x and solve. Now when we get into application problems, remember that we don't always have x's and y's. We can have whatever letters we want, c's, t's, whatever. So in general, to find an intercept, you're going to plug in 0 for the other variable and solve. And notice that for x-intercept, you plug in 0 for y. For y-intercept, you plug in 0 for x. We always plug it into the other variable. All right, so let's go ahead and look at some examples here. Example A, we have x minus y equals 2. So I'm going to go ahead and make a table. And we're just going to plug in 0 for each of our variables to find the other one. So for my x-intercept, I get x minus, plug in 0 for y, and solve. So if we do this, my y term goes away, and I am just left with x equals 2. So when y is 0, x is 2. For my y-intercept, I plug in 0 for x, and I want to solve for 2, or for y. So my x term goes away. I am left with negative y equals 2, and in order to solve for y, we divide by negative 1. So we get y equals negative 2. We have our 2 points, so we can go ahead and plot these. 2, 0 is 2 to the right, and it stays on the axis. 0, -2 is do not move left or right, you go 2 down. We end up here. And then we can draw our line. Want to go ahead and label our points. So our points are 2, 0, and 0, -2. All right, let's go ahead and look at example B. For example B, we're going to go ahead and do the same thing. We want to plug in 0 for each one of our variables. For our x-intercept, we're going to start by plugging in 0 for y. We get 2x minus 5 times 0 equals -10. My y term cancels, leaving me with 2x equals -10. Divide by 2, and we get x equals -5. For my y-intercept, we plug in 0 for x, my x term cancels, leaving me with -5y equals -10. We divide by -5 and we get y equals 2. All right, now that we have our 2 points, we can go ahead and plot them. -5, 0 is going to be 5 to the left on the x-axis, and we stay on the axis. 0, 2, we do not move left or right. We're going to go 2 up on the y-axis. We draw our line. And we label. All right, example C. We have y equals 3x minus 6. Note this is not in general form, but you still have x-intercepts and y-intercepts, and those are 2 things that we want to find. So let's go ahead and see what happens. Again, we're going to plug 0 in for each one of our variables. So for the x-intercept, let's see what happens. If we plug in 0 for y, we get 3x minus 6. We want to solve for x, so I need to add 6 to both sides. And divide by 3. So we get x equals 2 when y is 0. For my y-intercept, if you want, you can do the math. But as this is already in slope-intercept form, that second number is your y-intercept. So we get 0, -6 for our y-intercept. All right, so if we go ahead and plot these, 2, 0 is 2 to the right on the x-axis. 0, -6 is 6 down on the y-axis. We draw our line. and we label. All right, so that's using intercepts. So intercepts are very important. In the previous section, we talked about initial value. We also talked about it in terms of domain of application problems, being able to find those intercepts. And so these are going to be values that are important when we get into application problems. The last thing we're going to talk about is linear versus nonlinear. When we talk about linear equations, there's actually three options. The first one is exactly linear, meaning that there is a line that goes through every point. And this is what we've been working with so far. Everything that we've been working with, we do have a line that goes through every single point. The second type of linear equation is something we call approximately linear. When we get into the real life applications, is it necessarily the case that we have a line that fits perfectly with our points? And the answer is no. Approximately linear means that there is a line that comes close to every point. And the last one we have is not linear, meaning that there is no linear relationship, whether it be exact or approximate. There is not a line that goes through or comes close to every point. Not linear, for now, what we're going to say is that they kind of appear random. So if we look at the examples below, we have cheese consumption and fruit consumption. Cheese consumption, one of the things to note is that this is approximately linear. If you look at it and kind of squint your eyes a little, make it a little fuzzy, you can probably see that there is a line that's going to come close to every point. It may not go through every single one of them, but there is an approximately linear relationship between this. On the homework, you'll just go ahead and say that it does represent linear. Now, for the fruit consumption, this one, if we look at this, our points are all over the place. So this is an example of not linear. Now for this class, we are not going to actually find an equation that comes close to the points. We're just going to go ahead and state whether it's linear or nonlinear. And when we talk about linear, that means either exactly or approximately linear. Those would be considered linear. In future math classes, you will probably go ahead and use a calculator in order to find an equation that comes close to all the points. All right, that takes care of this section. Go ahead and work on the homework, and I will see you in the next section.